Hello, dear friends and colleagues. You see that in spite of coronavirus, eventually part of organizers of the seminars are together. I am very happy to have Slava now here with me. So, good morning, good day, good afternoon, good evening, and good night, especially for Tomoyuki, good night for you. So, we have today a difficult day. We have two talks. The first talk, it's a pleasure for me to present Professor Tomoyuki Arakawa. He will speak on Urod algebras and, well, Urod algebras, okay. So, are you ready, Tomoyuki?
Yes.
Okay, so you can start, please.
Thank you very much for the introduction, and thank you very much for the invitation. So I'd like to talk about Urod algebras and translation for W-algebras. This is a joint work with Thomas Creutzig and Boris Feigin. So please interrupt me anytime. So this is my first time to give a talk by Google Meet, so let me know if something wrong. So the plan of my talk is the following. I first explain what Urod algebra is, and then I talk about translations. These two motivations of this work, and then I explain main theorem, and then explain two main applications. So one is to define a translation for double algebras, and another application is the construction of higher rank Urod algebras. Okay, so Urod algebra was introduced by Bershtein and Feigin and Litvinov in 16, and Urod means a freak in Russian. So this is a very strange name. So let me explain what Urod is. So let G to be SL2 and take a standard generator E and H and F, and then consider corresponding affine Katsumori algebra. And I write xn to mean xtn, which is element here, where x is element of G and n is integer. And then I use the generating function like this. So anyway, Urod is just a basic representation of SL2 hat. So this is a irreducible highest weight representation of SL2 hat with highest weight lambda 0 in the standard notation. So this is generated via highest weight vector, and weight is given by the following. So the central element acts as 1, and H, which identify with H0, act as 0. So this is a weight of highest weight vector, and so this is one of the nicest representation of SL2 hat. So you may wonder why it has to be called Urod. So the reason is, so I would like to explain the reason. So this is in particular, this is not just a representation of SL2 hat, but it's a vertex algebra. And I don't really want to explain what the vertex algebra is, but it in particular implies that there's action of Virasoro algebra on this representation. So Virasoro algebra is another infinite-dimensional algebra satisfying this relation, and C is, of course, a central element. And usually, this action is defined for basic representation by Sugawara construction. And Sugawara construction for basic representation just given by this correspondence. Here, this is a normally ordered product. So maybe I will not explain the detail, but it's a very simple formula, and it satisfies this commutation relation. This commutation relation for with the element of SL2 hat, and this condition for the highest weight. So L0 in particular gives a grading on this representation, which looks as follows. So this is eigenvalue of L0, and highest vector has eigenvalue 0. So there's only one vector here, and for weight 1 we have, for example, E minus V0, H minus 1 V0, because this H minus 1 has add L0 is 1 on this element, and F minus 1 V0. And for the second level, we have something like E minus 2 and H minus square, and so on. So this is a standard grading. But so this is called Urod because we consider they consider different action of Virasoro algebra, which is given by following. So it's a bit complicated. So usually we have only this term, but they added this kind of element. So K is some parameter. And the point is that this has a different commutation relation with element of SL2 hat. So it has the following commutation relation. So commutation relation with this action has, so En looks like minus N minus 1, I think, and L0. So this is the same, but if you have this kind of a relation. So as a result, if you consider this grading, we have different structure. So on the weight to 0 space, we have this becomes two-dimensional. So V0 it still has eigenvalue 0, but also E minus 1 commute with L0. So this has weight 0. And on level weight 1, we have something like H minus 1 V0 and E minus 1 H minus 1 V0 and E minus 2 V0. This is all. And on the degree 2, we have H minus 2, for example, and also F minus 1 V0, and so on. So with this strange grading, this vertex algebra is called Urod algebra. So this is a definition of Urod algebra. So why they consider this kind of strange grading? The theorem is the following. So let Ck to be this this number. So k is some parameter which is not equal to -2, which is a critical level of SL2. The claim statement is that there is a vertex algebra embedding from 2 copies of Virasoro of vertex algebra. This is Virasoro vertex algebra with the central charge Ck. And this is another Virasoro vertex algebra with central charge Cl, where L is defined by this formula. So this embeds into this tensor product of Urod algebra with this Virasoro algebra with central charge Ck-1. So if you don't know vertex algebra, you don't have to care about it. The point is that if you have a representation of this algebra, there's 2 commuting action of Virasoro algebra on such a vector space. So, for example, if you consider a Varma module, so this is a Varma module of Virasoro with highest weight H and a central charge Ck-1, then there's action of this vertex algebra on this vector space, and if you tensor with this level 1 integrable representation of SL2 hat with highest weight nu, where nu is 0 or 1, there's action of this Urod algebra on this integrable representation. So this is a representation of this vertex algebra. And the first statement implies that there's 2 commuting action of Virasoro algebra with central charge Ck and central charge Cl. So you can try to decompose this representation as a representation of this 2 copy of Virasoro. And the result is that so this decomposes into a tensor product, sum of tensor product of Varma module of Virasoro algebra. For generic parameter. So K and for generic value of parameter, so this representation, the tensor product of representation of Virasoro algebra central charge Ck-1 with level 1 integral representation is a direct sum of a tensor product of Varma module of Virasoro algebra. And there are more statements, but today I'd like to talk about the meaning, a very interesting meaning of this decomposition. So this looks quite innocent, but it has a very nice geometric interpretation via a so-called AGT correspondence. So let me explain this. So I assume that the parameter are generic. And so Varma module has a L0 eigenspace decomposition. So this is So this space is so on here L0 acts as K plus D. And you can consider a so-called Guyot vector. So Guyot vector is a special Whittaker vector defined by the following property. So this has of this form. So this is an infinite sum of element of a homogeneous component of from a Varma module. So this belongs to a certain completion of a Varma module of the Virasoro algebra. And that is defined by the following property. So Ln, if you let act element of Virasoro algebra for positive mode, then this is GK HQ if n equals to 1 or 0 for n is greater than 1. So this means, in particular, if you let apply so it sends this means it sends L1 sends this component like this. So you can show that there's a unique up to constant multiplication a vector satisfying this condition for generic parameters. And this is called Guyot vector. And so-called AGT correspondence says that if you consider the pairing of Guyot vector with respect to a Shapovalov form of Virasoro algebra, which is by definition an infinite sum of a norm of homogeneous modes of Guyot vector. So this the AGT, so this coincides with so-called Negrasov partition function. So let me explain what is Negrasov partition function. So here M to N is a moduli space of framed torsion-free sheaves on P1 with a rank 2 and C2 equals to N. And N is, sum is taken over all N. So this is a non-singular variety of dimension 4N, which is equipped with action of C star to 4. So we can consider equivariant homology. And this is a class of M2N in the homology, equivalent homology, which is a module of equivalent homology of a point, which is just this low rounding. And by localization theorem, we consider this as a module of this quotient field. And so we can consider this as element of this space here. So AGT, so this means a Virasoro algebra somehow knows about the geometry of this moduli space, and so the Guyot vector precisely gives this element. So now the point now here what this decomposition means in view of AGT correspondence. So if we consider tensor product of Varma module of Virasoro with level 1 integral representation. Let's consider of highest weight 1. So we consider this is described as a direct sum of tensor products of Varma modules, two Varma modules. So now we can consider a Guyot vector here, and tensor with the highest weight vector here. This is highest weight vector. Now you can check quite easily that this is sum of tensor product of Guyot vector on the right side, on the right hand side. So this is a sum of Guyot vector, a tensor product of a Guyot vector, where CH, so this is some constant, and so beta 1, beta 2 is also constant too. So now, so this follows from the uniqueness of Guyot vector. And then if you take a norm of both sides with respect to Shapovalov form, you get the following identity. So on the left-hand side, because the norm of highest vector is 1, we just get Nekrasov partition function for this. And on the right-hand side, we get a product of two partition functions. And this is a non-trivial identity. And this identity, so what Bershtein and Feigin and Litvinov observed is that this identity is equivalent to so-called the Nakajima-Yoshioka blowup equation, which proved so-called Nekrasov conjecture, which is a statement on the regularity of the Nekrasov partition function. So to summarize, this innocent-looking decomposition is in fact equivalent to this non-trivial identity which follows from geometry. So now, so for SL2, I explained that this. So partition function is a sum of m to n, and 2 was the rank of the sheaves. But the statement of Nakajima-Yoshioka was more general. So the theorem applies not only for rank 2 sheaves, but also for rank R sheaves. And if you want to consider more general sheaves, what you have to do is you have to replace Virasoro algebra to so-called double algebra. This is double algebra, double R algebra. And so this is a statement of a Schiffman. And this is a AGT conjecture proved by Schiffman and Vasero. So it's natural to try to generalize to this higher rank case. The question we'd like to ask is how to construct a higher rank Urod. algebra. So this is one of our motivation. And now I'd like to explain another motivation. So this is a translation functors. So this is a very standard technique in representation theory. So I think most of you know very well, but let me explain a little bit. So let G be simply algebra, and let's consider a finite dimensional representation of G. And then we can consider the following functor. So if you have any G module, you can tensor with E and consider a diagonal action. So this gives a functor which is called a translation functor. So usually we project into a block, but let's ignore about this. And the nice thing about this translation functor is this is obviously exact, because we are just tensoring with a finite dimensional vector space. And this is really a fundamental tool in representation theory. And you can generalize this tool to affine Katsumudi algebras by replacing a finite dimensional representation with an integral representation. So we can define translation functor for affine algebra by as a tensor by sending M to the tensor product with an integral representation. So this is again exact, and this has a very nice property, and this is used by Kashiwara and Tanisaki and Feigin and so on to obtain an interesting result. And Goodwin generalized this construction for finite double algebra. So UG is a finite double algebra, is some nilpotent element. So UG is not, and then but he showed that if you tensor with module or UGE module with a finite dimensional representation of G, there's action, non-trivial action on this tensor product, so we can define such an exact functor. Because translation functor is very fundamental too, would like to extend this kind of construction for affine double algebras. But it's not clear at all with this Goodwin's construction can be lifted to the affine setting, because Goodwin used Scriabin's equivalence to construct such a functor, and the Scriabin's equivalence is not available in the usual form for the affine double algebras. Okay, so I have explained two motivations. So now I can try to state the main theorem. So now let's consider G to be simply algebra, and I take some nilpotent element F, and then we can associate with this data G and F certain one parameter family of a vertex algebra called the double algebra. So K is some parameter, So for example, if G equals to SL2, and there's only one conjugacy class for nilpotent element, and if level is not critical, then corresponding double algebra is just a Virasoro vertex algebra with central charge CK that is introduced by earlier. And if G equals to SL3, and if it's some root vector, which means that it's a minimal nilpotent element, and if K is not critical, then this double algebra is so the same as so-called Bershtein Polyakov algebra. And for G equals to SLN, and if it is the principal nilpotent element, and K is not critical level, then WTF is the WN algebra that appeared in AGT conjecture. And it's a bit it's not so easy to explain the definition of double algebra. So I just say a double algebra is defined by quantized Donifer-Sokolov reduction, which is a version of a Hamiltonian reduction. So the double algebra is defined by certain Biaristi cohomology called so this is a Biaristi cohomology for Donifer-Sokolov reduction. Which depends on the choice of nilpotent element, and the coefficient is it's a universal affine vertex algebra with highest at level K, which is just induced representation of affine Katsumori algebra, induced from one-dimensional representation of this parabolic algebra on which GT acts as 0 and K acts as this parameter K. The point is this is a vertex algebra. So that this double algebra has a structure of vertex algebra. And so the downside of this definition. So there are several definitions for double algebra, and so I prefer so this definition also this definition is not really a concrete. It's very abstract, but this has a very nice property. This definition is a functorial. So in particular, you have a functor from smooth G-hat modules, the category of smooth G-hat module of level K to the category of module of a double algebra, which is defined just by changing the coefficient to n for this Biaristi cohomology. And this functor behaves very nice if you restrict to appropriate category. So, for example, if you consider so-called casuistic parabolic category, O, which is a category of highest weight module on which the G, which sits inside G hat, acts semi-simply. So if you consider this category, then you can show that we have vanishing of cohomology for any object in this parabolic category. So which means that the functor from this parabolic category to the category of module over double algebra is exact. And many properties of double algebra can be obtained using this exact functor. So now, finally, I'd like to state the main result. So the statement is the following. So let V be any quotient of this universal affine vertex algebra. So this is a quotient vertex algebra. For any parameter k, and I take any integrable. So I consider tensor product of this vertex algebra with integrable vacuum representation. And then I consider a Drinfeld-Sokolov reduction with respect to the diagonal action. And the statement is that you can move this integral representation outside. This can be moved outside the Drinfeld-Sokolov reduction. And the point here is this is not as a not just an isomorphism of vector space, but also isomorphism of vertex algebra. So it's compatible with the algebra structure. And moreover, for any V module M and integrable G hat module N of level L, we have isomorphism, the same isomorphism. If you consider Drinfeld-Sokolov reduction with respect to the diagonal action, you can take n out of a coefficient as modules. So this is for all I of as modules over so this is the statement. So, and I should note that the isomorphism isomorphism of this two statement is as a vector space, it's quite easy to see. So the point here is this is isomorphism of a vertex algebra here, so that this is isomorphism of representation. So now I'd like to explain application of this result. So first application is the translation. So if you have if you consider tensor product of level K representation and level L representation, there is a diagonal action of affine Katsumudi algebra of level K plus L, and this can be stated as a language in the language of vertex algebra that there's a vertex algebra homomorphism from here to here. If for of course L is some integer, which is in fact embedding, and this induces by the exactness of Dirichlet-Sokolov reduction embedding from here to here. And this is by definition the W-algebra for level K plus L. And this is by a translation property. We can take this out of coefficient. So this is isomorphic to this is level L integral representation. And this is by definition double algebra for level K and integral representation. So we get so you have embedding of double algebra into this tensor product of these two. So in particular, you have a representation of this vertex algebra. There's action of this double algebra. So we get exact functor which is shift the level. So if you have integrable representation L of level L, so there's action of this integral of affine vertex algebra. So you have a functor from W algebra module for level K and W K plus level K plus L module for W algebra, which sends M to M tensor L. So this is exactly the translation functor for W algebra. For double algebra. Okay, so this is one application, and another application is a higher rank Urod algebra, as I promised. So for this, I have to assume that the G is simply laced. And then there's another description of double algebras, which is called coset construction. So I have to assume that the K is satisfy this property. So I forgot to say check with the dual Coxeter number. dual Cox eta number. And I define L to be a number satisfying this relation. And then statement either the double algebra. So this is a double algebra for a principal nilpotent element. This is isomorphic to GT invariant part of tensor product of these two. So this is so-called commutant of diagonal action. So I'm taking invariant with respect to the diagonal action of GT. So it's a commutant of G hat, diagonal G hat, inside of this tensor product of these two vertex algebra. So this means double algebra can be realized as an operator acting on here that commutes with the diagonal action for the affine Katsumori. And if you use this construction realization, we find that there's a map from PKG to W-LG to this tensor product. So this one is just a diagonal action. So this is a tensor product of level k minus 1 and level 1. So this the diagonal action has level k, and so WLG commutes with the diagonal action. So we have this kind of embedding. And if you apply Drinfeld-Sokolov reduction with respect to diagonal action, we get embedding of these two and so by translation we can put this outside, and so this is by definition on the left hand side, this is by definition WKGF. And on the right hand side, this we can put L1G outside. So this is the tensor product of WK minus 1GF tensor with L1G. So we have an embedding of tensor product of two double algebras inside WK minus 1GF tensor with L1G. So in particular, for principal nilpotent element, we have embedding of two principal double algebra inside tensor product of level k minus 1 principal double algebra and basic representation of G. And for G equals to SL2, these are Virasoro algebras. So this is exactly the statement of Urod algebra. So which says there's yeah. So it stated that there's a vertex algebra embedding of two copies of Virasoro algebra to Virasoro algebra and basic representation of G. And yeah, I forgot to yeah. So I forgot to explain that the one important thing for this statement, we have to be compatible with grading. We have to change. Needs to change grading to be compatible for the left hand side. And this change of grading is precisely changing the Virasoro action to Urod action. And with this Urod action, this embedding holds. And so this statement for SL2 is exactly the statement I stated in the beginning. And so now this is holds for any simply list G. So we get we have obtained higher rank Urod algebra. So in particular, in the same way, exactly in the same way as SL2, algebraic interpretation of Nakajima for G equals to SLR, Nakajima-Yoshioka blowup equation for rank R sheaves. Bit early, but I think I have said what I wanted.
Okay, thank you very much, Tomoyuki. Okay, are there any questions? Or comments? Tomoyuki, I have one question.
Yes.
For the basic representation for SL2, is a model for the Urod algebra.
Yes.
Now, if you take another representation for the simple vertex algebra, does it have action of Urod algebra as well?
It has to be level 1. I mean, what do you mean? Another so module for Urod. So U was basic representation, and U module is the same as I mean, we change the grading, but the same as module of this one. So this is nothing but the level 1 integrable representation of SL2 hat. Is that what you asked? So So this means if you want to consider, so this is arbitrary level. If you put L equals to 1, this is integral g hat modulo of level 1. So in general, L G module is just a level L integral representation of G hat. I'm not sure whether I'm answering the right thing.
Right, and the Urod algebra X on any LK module.
Yeah, it acts on any. So if you consider this as a Urod, it acts on any level L representation. Yeah. But of course, we consider different strange grading, but still it.
Okay. Okay, any other questions? If not, so let's thank Tomoyuki for a very interesting talk. Thank you very much again. And we'll come back in 1 hour for the second talk.